So we're concluding the chapter here by kind of looking at, from a construction standpoint, how all of this comes about. So we've talked about this idea of molecular shapes and how these electron pairs are being arranged in this three-dimensional space to create these shapes that minimize repulsion. But we really haven't gone through the explanations of why this occurs or how this occurs. And that's what today is all about. Now, to kind of set the table for that, we have to understand that when it comes to chemical bonding, there are two different types of bonds that can form. The first is a sigma bond. A sigma bond is the creation of a chemical bond through the direct overlap of two orbitals. So think back to what we've talked about in terms of atomic orbitals. Go back to chapter 3. You have your s orbital, which is spherical. You've got your p orbitals, which are dumbbell shaped. You've got your d orbitals and your f orbitals and so on. When those orbitals overlap each other directly, that is called a sigma bond. And that is the strongest kind of bond that you can have covalently, because the electron densities are overlapped with each other. They are intermingling directly. There is another type of bond that can exist, though. It's called a pi bond. Pi bonding exists not as the direct overlap of orbitals in a linear kind of circumstance, but rather the parallel overlap of orbitals. In particular, we talk most about p orbitals doing this, but the parallel overlap of those orbitals with each other. Now, it's hard to kind of simulate what that orbital looks like and what that pi bond looks like kind of in realistic terms, because we've seen the pictures and we know that from a pictorial standpoint, okay, a sigma bond makes sense. Yes, we've got one p orbital, and we can see that a second p orbital overlaps it. There's our direct overlap. That is our sigma bond. But in p orbitals, for pi bonding, we look at these and we say, okay, yeah, I can see that they're in parallel, but why can't I just overlap them this way? No big deal, right? The problem here is repulsion. To simulate that repulsion, here's what I want you to do. You are going to pretend that your forearms are p orbitals. So hold them out in front of you like you're defending yourself in a boxing match. Now, it's easy to do it like this. Try to put them together next to your chest. Try to make your elbows touch. Not so easy, is it? You've got resistance in your chest. The same thing is true in these p orbitals. They've got a nucleus in the middle. That nucleus is full of positive charge. And those positive charges don't want to interact with each other, don't want to get that close to each other. Repulsion pulls those apart. So what we end up having is we do have some overlap above and below, but they can't get nearly as close to each other as a sigma bond can. So the interaction, the overlap is not as easy. And because of this, we're not going to see pi bonds on their own. What we're going to see is pi bonds will come about if we already have a sigma bond in place to supplement that sigma bond. So what does that mean? That means that we really only see pi bonds when we have double bonds and triple bonds. That first bond is a sigma, direct overlap, and then any additional bonds after that are pi bonds that exist in parallel above and below that sigma interaction. I want to pose this question to you because you probably have thought it at one point in time over the past week. How is it possible that if I have 8 valence electrons that I'm striving for, how do I get to those hypervalence states where I have 10 valence electrons or 12 valence electrons around that nucleus? Moreover, thinking about things now from this valence bond theory idea, if the s orbital is capable of sigma bonding and the p orbital that exists in that middle axis can sigma bond, we know that the other 2 axes can't. How do we get 4 covalent bonds then without having everything make a double bond or a triple bond? So I'm posing this question to you. I want to see what kinds of ideas you might come up with for why we can make even more than 2 bonds at a time. So think about it, put an answer in here. Let's see what we come up with. So everything we've talked about has been in kind of the framework of this idea of repulsion and minimizing repulsion. How that comes about is through something called hybridization. So put this in the category of, I told you a story once and now you know me to be a liar. Welcome to chemistry. Hybridization basically says, you know, all that atomic orbital stuff that we talked about in chapter 3? Yeah, that only applies if it's an atom. As soon as it bonds, all that changes. Hybridization is the means by which we do that. So what happens is this. As an atom goes into forming bonds to make a molecule, what it is going to do, it's going to transform its atomic orbitals in such a way to minimize the repulsion to create the molecular shape that's necessary to minimize that repulsion. We can kind of think of it as taking those atomic orbitals and putting them into a blender and coming out with these new orbitals that are a mixture of the two that also happen to be oriented exactly at the angle that we need them to be. So those mixed up orbitals, those s orbitals and those p orbitals that we put in there to create these shapes, we call those hybrid orbitals. And I'm going to show you pictures of them. You will find that those hybrid orbitals contain characteristics that look kind of like s orbitals and kind of like p orbitals at the same time. And the net result, that gives us that shape, we call that hybridization. Now, these hybrid orbitals always form in sets. And what we're going to find is that not only is there a unique set for every electron group arrangement, steric number is going to dictate to us the hybridization that we will use. So there's a reason that we taught you this in this order. And the order here is, if I can identify the steric number, that steric number tells me two things. Tells me how many orbitals I need to throw into the blender and what those orbitals are going to be. And as a result of that blending up of the orbitals, I'm going to pop out this molecular shape. We know those molecular shapes: linear, trigonal planar, tetrahedral, trigonal bipyramidal, octahedral. We talked about them already at length. Now we have the means by which we make them. So how does the atom create those shapes? Hybridization does that. So we're going to show you a series of pictures. What I want you to understand out of these pictures is that when it comes to the center atom, we can take its existing electron configuration and reconfigure it to give us the correct number of orbitals and the correct number of bonds necessary for the molecule that we're about to draw. How that comes about is really pretty simple. In our hybridization, single electrons are going to turn into bonds. Double electrons are going to be our lone pairs. And so as we move through this, we'll be able to kind of see, oh, that's how we end up with tetrahedral for ammonia. And here I can see the ammonia's got a pair of electrons and 3 unpaired. That's where the 3 bonds are going to be. That's where I'm going to make my 3 sigmas. Hybridization allows us to create those orbitals that can have sigma interactions and make sigma bonds, so we don't have to worry about pi bonding. So we're going to start with Sp3 hybridization. Sp3 hybridization is steric number 4. And the reason we're going to start with this one is because it is the most common hybridization. So how do I get 4 orbitals to match my steric number 4? Well, we always start with an s orbital because it's the lowest energy. An s orbital plus 3 p orbitals gives us 1, 2, 3, 4 orbitals. We throw those 4 orbitals into the blender, and instead of having an s orbital and 3 p orbitals that are at the cardinal axes, we end up getting 4 orbitals that are all 109.5 degrees apart from each other to give us that tetrahedral. And with that tetrahedral, we can now see that when it comes to interacting with the 1s electron from the hydrogens, these occur and have direct overlap. So I've got a sigma bond there, sigma bond there, sigma bond there, sigma bond here. All of those bonds are sigma bonds which is exactly what we needed. Because you can't have bonding unless you have a sigma bond first. So hybridization is going to give us the direct means for making sigma bonds. Because it's going to push those electrons far enough away from each other that we're going to minimize repulsion, and we're going to have a means to have that direct overlap instead of parallel. Other common sp3 examples, again, dealing with steric number 4 here. We see nitrogen. Nitrogen has 5 valence electrons. So if I spin those into 4 hybrid orbitals, I end up getting a pair of electrons and 3 unpaired electrons. Those 3 unpaired electrons will go on to make sigma bonds. That unpaired set of electrons still gets put into a hybrid orbital because we need it to be minimizing repulsion. But I can now see, okay, it's in this scheme. It's part of those hybrid orbitals. It's going to push down on the structure, though. That's why we end up getting those bonds that are, less than 109.5 degrees. In the case of ammonia, I think it's 107. For oxygen, I can see that I have 6 valence electrons. So 6 valence electrons getting pushed into those 4 hybrid orbitals. I end up with 2 sets of pairs of electrons. Those go in hybrid orbitals. I have 2 unpaired electrons that are going to make sigma bonds. And so that's where we get the structure of water. That's how we determine that water has that bent structure and that its bond angle is somewhere less than 109.5 degrees. In this case, we know it to be like 104.5 or something like that. So let's move on to Sp2. Sp2 geometry, this is where we have steric number of 3. In Sp2 geometry, since we only have a need for 3 hybrid orbitals, we're going to throw in an S. We're going to throw in 2 P's. That's going to give us 3 in total. Now, since the valence shell includes 4 orbitals, but we're only hybridizing 3, we're going to have 1 orbital there that is unhybridized. Depending upon the circumstances, we are either going to see that unhybridized orbital as completely empty, as in the case for like boron and aluminum and some of those group 13 covalent compounds, where they break the octet rule by going under. Or what we see more commonly is that that unhybridized p orbital has an extra electron in it, and the purpose of that extra electron, we have a double bond somewhere. So unhybridized p orbitals, these are what are going to make pi bonds. So if we are looking at the hybridization scheme of the carbon, carbon has 4 valence electrons. They are being distributed over 3 hybrid orbitals and the 1 unhybridized orbital. We're going to see that they split evenly, which means the carbon's going to make 3 sigma bonds. And 1 pi bond. And if I look at the carbon, I can see that. I can see it's 3 sigma bonds. And then its extra bond here is its pi bond. We can also look at the hybridization of the oxygen. Now, we haven't looked so much at molecular shapes for non-center atoms, but there are occasions where that it is a relevant thing to look at. And we follow kind of the same rules. We can determine the steric number of a outer atom the same way. The number of atoms it's bonded to, which is usually just 1, plus the number of lone pairs that it has. So in the case of the oxygen here, again, our steric number is 3. It's bonded to the 1 carbon, and it has 2 sets of lone pairs, steric number 3. So it needs 3 hybrid orbitals as well, which means it's going to have 1 unhybridized p orbital also. Thing is, it's got 6 valence electrons to distribute instead of just 4. So how do those 6 distribute? Well, 4 of them are going to make lone pairs. 1 is unpaired, so that's going to be its sigma bond. And the remainder here is going to make a pi bond. The 2 unhybridized orbitals here, they make the pi bond between them. Everything else makes sigma bonds around it. So how does that look in 3-dimensional space? So here is a model of that formaldehyde using space filling kinds of ideas. What we can see is that we've got our sp2 hybridized carbon atom here, and we're going to see that it's going to make sigma bonds with the 2 hydrogens and a sigma bond with the hybrid orbital of the oxygen. But these unhybridized p orbitals aren't going to be able to get close enough to each other to actually form sigma bonds. They're going to have to form a pi bond instead. They each have 1 electron in them. So the pi bond is going to form in parallel over that sigma bond between the 2 hybrid orbitals. That's how we get that double bond. For sp hybridization, we're talking about steric number 2 here. Now, sometimes with steric number 2, we're talking about just literally a linear molecule. We've got 1 kind of, easy bond between 2 atoms, not too terribly difficult to see. But if we have something more complicated, like a carbon that is undergoing multiple bonding situations, 2 double bonds or a triple bond, what we'll see in that circumstance is with a steric number of 2, I only need 2 hybrid orbitals. So I have an s orbital and a p orbital that hybridize. The other 2 don't. And so what I get are 2 sigmas and 2 pi orientations. The carbon atoms each interact with a hydrogen and each other in these sigma orientations. And then what we see is that we'll have pi configurations above and below, as well as in and out. Because we have two sets of p orbitals that are interacting. The ones that are going this way, so that's our up and our down, and then the ones that are going this way, the ones that are going out toward you and in toward me. So that covers the majority of the hybridization that you're going to see. Most hybridization occurs in linear, trigonal planar, and tetrahedral kinds of configurations. Now, we do know that those other two shapes exist, the trigonal bipyramidal and the octahedral. What has to happen there is, because we're talking about the formation of 5 or 6 electron groups, 4 atomic orbitals are not enough to cover that. So we have to integrate a 5th atomic orbital or a 6th atomic orbital. Where do those come from? Well, they have to come from the D sublevel. And that's why we don't see oxygen or nitrogen or fluorine showing this kind of behavior, because with their valence electrons in the second energy level, the next closest D sublevel is the 3D, which is practically 2 energy levels away. But for phosphorus, sulfur, and anything below it, yeah, the third energy level, I've got the S, I've got the P, I've also got the D sublevel. And yes, that D sublevel is technically a little bit higher than the 4S. We also know from all of those exceptions to the configurations, they're really close to each other. So in a pinch, I can throw in a couple of extra D orbitals to help minimize the repulsion. So what does that look like? Well, for steric number 5, we're talking about Sp3D hybridization, that 5th orbital coming from the D sublevel. And for steric number 6, it's Sp3D2. I need 2 of those D orbitals to help get us up to 6. Now, again, we won't get too deep into those, but we can kind of make the same kind of schematic arguments with them that we made with the others. I have, for phosphorus, I have 5 valence electrons. I'm distributing them over 5 hybrid orbitals instead of the atomic configuration where some of them are paired and some of them are unpaired. They all become unpaired in the hybrid model. That allows phosphorus to make 5 single bonds. Just like that. Five valence electrons turn into 5 unpaired electrons in those hybrid orbitals. Those unpaired electrons would allow us to make 5 sigma bonds. For sulfur, I have 6 valence electrons. If I turn it into 6 hybrid orbitals, Sp3D2, all of them now become unpaired. I can get 6 sigma bonds as a result. And obviously, with the addition of charges, we can see that changing as well. So negative charge, we'd add an extra electron into the scheme. Positive charge, we'd take an electron out of the scheme. And that would explain in some ways, okay, this is why a double bond is forming here, or this is why a single bond is forming there. This is why we have an extra pair of electrons on the sulfur or on the selenium, and this is why we don't. The big takeaway that I want you to walk away from this with is this. Everything ties back to what we already talked about. So I know for a lot of you, your heads are kind of spinning right now because from a theoretical standpoint, this is very difficult material to kind of put your head around because it's requiring even more visualization than what we were even doing with Vesper theory. Now, this table is one of the tables that you're going to get for the chapter quiz. And what I want you to think about doing mentally is understanding that there is a direct tie between the steric number of your shape and the hybridization that it's going to take on. And so they're all interwoven and interrelated. Don't think of these as separate concepts that you need to compartmentalize and memorize individually. If I draw my Lewis structure and I determine from that structure that the steric number is 4, automatically I can do two things. I can say, oh, with a steric number of 4, its hybridization is Sp2 and its domain geometry is tetrahedral. Because those three concepts, domain geometry, hybridization, and steric number, are all talking about the same thing. The only thing I have to memorize or look at from that standpoint after is differentiating between lone pairs and bonding pairs in my structure. That's all I have to do. Now, this table attempts to kind of go after that by asking you to count the number of sigma bonds, understanding that if you have the same number of sigma bonds as the steric number, then the domain shape and the geometry are the same. And for every sigma bond that you are lacking, that's a lone pair that you have. And so this table looks very, very, very similar to the table I showed you on Wednesday. All right, let's do an example here. Look at the hybridization of carbon and oxygen and carbon dioxide and describe the types of bonds. So carbon dioxide has a Lewis structure that looks like this. So we're going to evaluate each piece here. And the way to evaluate it is calculating steric number. So for this carbon, I can see that it is bonded to 2 different atoms. It has no lone pairs. Steric number here is 2. With a steric number of 2, we are talking about sp hybridization and a linear shape and a 180-degree bond angle. For the oxygens, now the 2 oxygens in this molecule happen to be identical. They're both double bonded. But I can still evaluate their steric number. It's bonded to a carbon, so that's 1. And it has 2 lone pairs, so that's 2 and 3. Its steric number is 3. Steric number 3 means Sp2 hybridization. Sp2 hybridization means trigonal planar domain shape and roughly 120-degree bond angles. Now we know with the lone pairs there that's going to shrink things a little bit. The reason we don't have a particular name for this shape is we don't have one for 2 lone pairs. It's, I guess we would call it linear, since there's only one bond to speak of. This is also why we usually don't do molecular shapes of exterior atoms. We usually just focus on the center. Now, in terms of the types of bonds here, we know that there are 4 bonds in total. We can count them. 2 to the one oxygen, 2 to the other. We know, because that there are 2 atoms here, that 2 of those bonds are sigma. Sigma to the left, sigma to the right. Simple subtraction will tell us that naturally the other 2 have to be pi bonds. Now, the other way we can do that is we could count it. I see that I have 2 double bonds there, so that would mean I'd have 2 pi bonds as well. So that is all for this chapter. And I know I threw a lot at you here today, so I'm expecting a fair number of reds and yellows here, but give me some feedback on the way out. Hopefully after Sunday, some of this makes a little bit more sense just because you've done the skill builder, you've done the homework assignment and the post lecture. Hopefully we can start piecing it together, getting things out for Monday. I'll give you another chance to ask questions on Monday before we move into chapter 6. Have a great weekend.